How's everybody doing? Welcome back to the channel, and today we are going to test the MetraHit IM Xtra on my motor winding simulator over on the right hand side of the picture there. What I'll also do is show you the connection to the Metralog software running on the tablet so we can record some results with that. For a standard motor test, I would start off with measuring the winding resistance. Our IM Xtra here can do that in both 2-wire and 4-wire mode. We'll do 2-wire mode to start with, and then we'll do a 4-wire mode to see how that compares. So to enable Bluetooth connection to the tablet, you go to the menu button here, the general setup, we go up to interface, and we hit OK, and OK again, and then you can turn Bluetooth on and off as you desire. You do have a pin number there, standard pin number that comes with the instrument for the initial connection. That's already been done. I've already paired the instrument, so we're all okay there. We click OK there, and then we can escape back to our measurement function. Hit the Metralog software on here. As you see, we've already been paired at the top here, so we'll hit that one there. And you can see we are on the ohms function there. So with the Metralog software, you can change the display from the old analog display there to a digital display, and then to a time graph as well, and then back to the analog display there. So we better zero the instrument first, haven't we? Let's go on there, hit the start button, and see we've got 0.078 there, which is all nice and steady. We'll hit the zero function there, and we've zeroed. You can see we've gone to 0 on the tablet, but it doesn't tell you that you are actually zeroed the instrument, like it says at the top here that you've zeroed and what your offset is. So we'll connect up and see what we get. Our winding simulator is in delta configuration, so we are looking at 1.17 ohms, and for our first two phases, U and V there, we are 1.18 ohms. So what we can do is record that value there, and then if we change over to our next two sets there, and we've got 1.186, 1.182 on that one, going down a little bit more. That's steady. We'll go to the final phase, see what we get there. It's a little bit finicky. 0.19, coming down a little bit. 0.194 there, so reasonably balanced. Let's turn off our record function there, and then we can put in a name for this. Do the original test one for mine, and that's our 2-wire connection. So just unplug them, and then we'll, pardon me while I change over to 4-wire measurement. So we need a different set of leads. So as we change to our 4-wire measurement on there, you'll see our 4th jack will become available. So we'll be able to put a connection into that one, and you can tell that our display has now moved over to a milliohm function there. So as our first lead, now you do have to be a little bit careful with the connections on this because they are spaced apart, they're not together. We've got our source there, and then our sense for the positive terminal. Over there, we can plug him on there, and then do the same with the next lead. So we've got our source in the, and our sense one is over there, and then we'll put them on the other terminal there. No zeroing function on this because we are on 4-wire measurement. We do have a T-comp there, however T-comp is thermocouple voltage compensation and not temperature compensation. So you can use that to take out the very small voltages that sometimes appear when you've got different metals and you're putting a test current through them, so the differential between the bolted connection that you see on there and the crocodile clips, the metal of the crocodile clips. However, with 1.17 ohms, it's not going to make any difference to this test. We do have changed the current on this. We can go up to 1 amp. However, 1 amp is a pulsed measurement, so that's not really for winding measurement. That's for the measurement of bolted connections and the like. So your 200 milliamp and your 20 milliamp are constant current, so we'll leave it to 200 milliamp as they will measure inductive loads a bit better, which is what a motor winding is. So we've got that measurement there. We'll hit start again and see where we get to. 1.184. Okay, let's go to our record there. We can record him. You can show one that's gone there. 1.168 on that one. And then our final phase. 1.181. So reasonably balanced across the three measurements there. We'll hit our stop button on there and we'll give this equally test 2, equal the original name. So that's the winding resistance measurement made there. And then we can get rid of our leads onto a stop, and we can set up for insulation test. I need to remove these leads, and then we can go back to our original set of leads and set up for an insulation test. Let's do that's there, that's there, and then for our insulation test we also have one on the winding, and we put the other one onto the earth, what would be the motor frame. And we can go all the way back around to our RISO. So we do have a bit more capability with our IM Xtra. We have a standard insulation test function. However, we also do have DAR and Pi. To get to them, we use the function, but the function takes you through the coil test. I'm not going to do the coil test in this video because my motor winding simulator doesn't respond to the coil test. But what you'll see when I hit the function button, it goes over, the software kicks out, it doesn't like the screen. The actual Metralog software is for the IM Ultra. There isn't specific software for the IM Xtra, so you do lose the coil test measurement with the Metralog software. However, if I press it again and go to DAR, you can see we come back and it does recognise it as DAR on the screen. And if we go to function there, we can get to polarization index. It doesn't record the pair, so if you're on polarization index, all you get is that one value. To go to the DAR, you have to do a specific DAR test if you want that. But obviously we can record the values as we go along, and we could manually extract the DAR ratio during a Pi test. So we'll stick to our record function and kick him off, and we're on 500 volts, and we hit the start. Now what you do get is the instrument's kicking out 524 volts, but the timer hasn't started yet. So what I've found is you do get a slight difference in the nominal values from this against what I was getting from other instruments. So we can let that run through the test. In the meantime, I can show you a couple of screens from other testing that have been done. This is the overall graph for the insulation test accuracy. You can see there over all the ranges, you've kind of got a theme to it there at sort of 90 to 100 mega ohms. It changes from a predominantly positive error over to a negative error, and that's on all of the 5 test voltages there. They're fairly consistent in operation, but the readings are all well within the tolerance of the IM Xtra there for insulation testing. Pop this screen up here. This is the average accuracy for all of the tests compared to all the other instruments that I've tested, and this comes in at 0.306% average accuracy, putting it in the top 50% of all the instruments that I've tested. That kind of accuracy is more than adequate for motor insulation testing there. So all well and good with that one. So our next plot, this is looking at just the voltage and current output from the test instrument for each of the ranges. See our equivalent open circuit voltage there is all within 20% of our nominal test voltage, which matches the specification for the IEC standard. Our short circuit currents are all 1.13 milliamps, really. Pretty good consistency across each of the test voltages there for the short circuit currents. Again, it's 1 to 2 milliamp usually you see on these instruments. You can go up to 15 milliamps on the IEC standard. And then our 1 milliamp load test there, and we need to be exceeding 1 milliamp for the relevant load on each of the test voltages, and you can see there we are just slightly above that, so all is good with that one. So unfortunately our camera battery went flat during the test, so we haven't been able to make a full recording of the polarisation index test, but it's not much of a spectator sport anyway, so I don't think we've missed anything. We're coming up towards the end of the test now. Got another 30-ish seconds to go, and you can see a fairly traditional sort of curve for a polarisation index test, and that does match the model that I have for this. But once we've got all the results, we will be able to do a comparison to the model within Excel. You can see down the side here, as we're doing the test, we do get test voltage. The actual nominal voltage was set to time. It's recorded the initial reading of 4.53 mega ohms there, which is comparatively high. So you can see we have finished the test now. We have switched to a voltage measurement at the end of the test. Because of the nature of my simulator, it's very capacitive, so it does store a voltage. So I'm just going to drop the lead off just to get rid of that, and then we can get back to the screen there. So here we have our results. Shall we see if we can bring him forward and zoom in? Okay, so we're focusing on the screen itself. You can see we've got a fairly standard curve for a polarisation index test. I'll compare that to the model I've got in Excel for my simulator at the end. We do get the test voltage being measured at the time. Obviously it's 0 volts at the moment because it's switched off. Our nominal setting there, the time gets ramped up during the test there. And then we have our initial reading at 1 minute there of 4.53 mega ohms, and a final reading of 32.8 with a polarisation index of 7.25. We do have a nominal polarisation index of 7.76 for the simulator based upon my model. That the differential is due to this 4.53 mega ohms of the 1 minute reading. 32.8 is about right for the 10-minute value. As I pointed out when you started this test off, it seemed to apply the voltage, so we actually are going under a test, and then the timer was a little bit slow to initiate, therefore the readings are a little bit out based upon that. When I compare it to the model, we'll be able to see what the 1 minute value should be instead of that 4.53. I believe that's where the differential is. So when you've finished your recording and you've got all your data, you can then retrieve that data from going to the logs, which is in the bottom right hand side here, and then it lists the tests that you've carried out, the data that's been saved. You can select the one you want. It immediately takes you to the graph. The graph here is expanded out over 1 minute, but you can shrink it back down, which interestingly you can't do during the test. You're just left with the 1 minute window during the test. However, hopefully what you can see, there's a couple of spikes here on the plot that it's given me. I believe those spikes are due to where the meter changes range and it momentarily loses the actual insulation resistance value and replaces it with an overrange value, which isn't particularly brilliant. And the alternative to the graph is to go to the actual data itself, and in this table format you can see it's just got the time and the actual insulation resistance value it recorded. You can see here for the first 3.5 seconds it hasn't recorded any value at all. It is recording every half a second, so it does give you over 1200 data points for a polarisation index test. You can scroll through these. Not sure whether they see there it's OL. where it's gone over range. So there's the OLOLO down there. And if we go all the way down to the bottom, well, there's its final values. Again, it loses values. It knows, the meter knows the test is completed, but the recording facility on here doesn't. It just keeps recording until you manually knock it off. So again, which isn't brilliant really. The other thing that you notice here is that it knows it's on pi, but it hasn't recorded any pi value or any dar value as part of the data. So kind of where we are with the data collected by the tablet. Once you've got this data, let's go back out again so you can see down here at the bottom. We can go and hit that, and it gives me the option to send to mail, send to OneDrive, or export it as a file. So it will export it on mail as a CSV file in a zip format. So if you've got multiple files that you're sending out, it will actually amalgamate them all into the one zip file, and they all get sent under the same file. Okay, so we're at the computer, and we'll take a look at the winding resistance measurements first. You've got a table for the open winding, star winding and delta winding configurations. Top rows are nominal values. You have the actual measurements that I made, and then we've got percentage of deviation from the nominal and percentage of deviation from the average. Because it's the simulator that I built up, I know what the nominal values should be. Therefore we can look at that percentage deviation from the nominal as a good comparison. However, if you're actually measuring a motor winding, it's very rare you will have the nominal value. Therefore your deviation from average is the more relevant figure to look at. But as we look across them, they are all for percentage deviation from nominal. I'll be looking to be within at least 5% of the nominal value, plus or minus 5%. And you can see all the figures fall into that band, whether it's the 2-wire measurement or the 4-wire measurement. Possibly the worst measurement is on the delta for the V to W phase, is 2.05% out on 2-wire measurement. Interestingly, it was 0.17% under for the 4-wire measurement. And then deviation from average, our worst figure for that is minus 1.21% for W phase on the 4-wire measurement. Deviation from the average value I'd look to be within plus or minus 2% for that kind of measurement. But overall, yeah, they worked out pretty much okay. I don't really see that much of a benefit from the 4-wire measurement. You're not getting any more resolution for the test that I did here, so not that much value really. Probably when you go under 1 ohm winding resistance that the 4-wire measurement will come into its own then. Pretty happy with the way those measurements turned out and the operation of the IM Xtra for that function. So looking at the data that gets uploaded from the tablet, it comes into Microsoft Excel as a CSV file. This is the raw data that you get. So you see it records the time in seconds, and then the next one is the value. You get your min and max range raw data column, which is a repeat of the value column, although that's not saved as a number. And then you've got a couple of other extra columns here. Could well be time and date again that hasn't formatted correctly, but I haven't looked into using those ones really. I've concentrated on these first 2 columns here. So that's what your raw data looks like. Again, bit of file information, meter information, date and time, and the function, but that's all you get all the way down through, all the way down to the end there. And you can see there's no pi ratio value from any of the data. You'll have to calculate that yourself. So what I did, I don't need 1200 entries for a polarization index curve, so I copied that sheet over and then I played around with these values. I take the 15, 30, 45, 60 second and then at 1 minute intervals up till the 10 minute there. This is the original data that you come down, and you can see I got a DAR of 1.62 and a pi of 8.29. I then used various different time shifts to try and cater for this section of time when the test seems to start, but the instrument times it differently from a different point. So these are the delay, 4.5 seconds, 6.5 second, or an 8.5 second delay. And you can see the relevant values I've got there. The actual comparison to model curve. So from the model, the DAR is 1.63 and the PI should be 7.76. So the base data from the IM Xtra gives me a DAR of 1.62 and an 8.29. The curve seems to follow pretty well. It's the blue curve that's the model, and the IM Xtra is in the orange. It's okay, but obviously it doesn't follow it reading for reading. There's slight differences at the 30, the 60 second, and at the 10 minutes. That are all the values that you need for the ratio values. To get to a pi of 7.76, the closest I got was a 7.86 there with a 4.5 second shift. However, that drops the DAR down to 1.55 then. So yeah, there does seem to be a little bit of an issue with this PI function on the IM Xtra and how it records the data, and not being consistent with what my expectations are. So that's covered the testing of our little motor winding simulator using the IM Xtra here, the installation functionality, and the 2-wire and 4-wire for winding resistance measurement. Reasonably happy with the operation of the winding resistance measurements, but as you've seen, there is a bit of an issue with the way the polarization index function worked with that simulator. I'm not sure why the instrument is given a bit of a delay to recording the measurements, and subsequently the effect that has on the DAR and PI ratios. I'll try and do some more testing on some of the other simulators that I've got to see if it operates in the same manner as that, but it is a little bit disappointing. That's it for this video. Thanks for watching. I hope you found it useful, and I'll see you again in the next one.